पानी ठंडे पानी नहीं पानी का बस Rosa, actually, you tell me when I should start.
You can start.
Should I start?
Yes.
Okay. So, good morning, all of you. I'll be talking on particles form optimization. Afterwards, I'll also talk about ant colony optimization. Both of these optimizations come under so-called swarm optimization. Okay. Am I audible? My screen is visible to everybody?
Yes.
Okay, fine. So, particles form optimization, it has a very interesting history. It was proposed in 1995, and within no time, it became absolutely popular. The history is like this. There are two friends, Professor Russell Eberhard, he is from electrical and computer engineering, and another Professor James Kennedy, he was social psychologist. Both were friends, and they were taking their lunch together, and while doing that, they were chit-chatting, and on their table there was one vase, glass vase, wherein they had fish, a number of fish. So if there is any leftover, they will put it in that vase, and they noted that immediately they put something in the vase which is eatable. The fish there will scramble and go towards the food item. So this was very interesting. They saw it quite almost daily. Then Professor Eberhard, who is a computer sort of division, he thought of making a screensaver. Kindly look here. The whole intention was to make a screensaver. Then he went on trying to do that, but he did not know how the fish behave. So social psychologist Professor Kennedy butted in, and both of them together made a screensaver. But they realized what they have made is particles form optimization. So I hope you feel interested. Now, what exactly is particles form optimization? We feel that birds, fish, ants, they don't have that much of intelligence. But if they are in a group, they show a lot of intelligence, right? So, for example, you can see here, they are flying together. And if there is any food item on the ground, they will zoom towards it. Now here you can see a swimmer. He is in a sea, but as soon as the swimmer is there, all the fish move away from him. Now, the behavior is that of a group and not an individual, but if you think each individual has limited capability, but as a group, they behave in a very intelligent manner, right? So, 1 minute. Now, particles form optimization, what is popularly known as PSO, tries to imitate behavior of flock of birds, school of fish, swarm in general. So when we talk about particle, it can be bird, it can be fish, it can be swarm in general. As far as our engineering thing is concerned, particle means if you are designing something and if there are say 20, 30, 40 options, each option you can consider it to be particle. Okay, so the meaning of particle has to be understood in that sense. Now, we'll have the question when to use particle form optimization, when to use simulated annealing. I suppose you have not been exposed to simulated annealing. I'll just tell you, simulated annealing stands out as one algorithm which is non-greedy. Now, I'll just explain this non-greedy. In fact, since I had talked to you about genetic algorithm, I have forgot to mention one or two things there. The point is that genetic algorithm is known to be a greedy algorithm because of the fortune wheel or that roulette wheel, which I talked about last time. Because the roulette wheel is biased towards the fitter candidates. So therefore, it shows some sort of greed. Whereas simulated annealing is sort of absolutely non-greedy. Even if you give him the best design, it will reject him. And it will say that, hello, don't try to fool me. I'll use my own intelligence and then grade you, right? So simulated annealing is probably to my knowledge, is the only algorithm which is non-greedy. Therefore, it will give you quite accurate answers. Now, genetic algorithm is greedy. But please note one thing. When I say greedy and non-greedy, it is in a conventional sense. For example, if I say Ferrari, what will come to your mind? A car going at very high speed. Am I right? Yeah, I would like some response so that we get into interactive mode. Yeah, but don't you believe that if a person, the adept driver who is driving Ferrari, if he notices his friend is walking near, sort of along with, he can slow down it so much so that he can talk with the friend who is walking along with him on the roadside, and he is in a car. So it means that even though Ferrari is associated with a lot of speed, still an adept driver can make it as slow as possible. So in that sense, you have to accept these categorization. So when I say that the simulated annealing is non-greedy, it doesn't mean that if a person wants to make it greedy, he can do it, right? Similarly, genetic algorithm is known to be greedy, but if a person wants the genetic algorithm to be non-greedy, he can do that. But these are rare instances, correct? So as I said, Ferrari, nobody will use it for going at a speed of a person walking. That you usually don't do. So whatever I talked, it has to be understood in the general sense. So I'll repeat my sentence. Simulated annealing is non-greedy algorithm. Genetic algorithm is greedy algorithm. And these two algorithms are most popular, and they sort of occupy a very top position in the algorithm alternatives. And I would say that both are equally powerful provided they are handled by capable persons. So nobody can say that simulated annealing is better, or nobody can say that genetic algorithm is better. It depends on who is using them. Okay. And then finally, it boils down to personal convenience and sometimes the limitations imposed by the computer. Now let us talk about particle swarm optimization. I think I did mention in my genetic algorithm lecture that particle swarm optimization is to be used when you are dealing with a huge problem and you want somehow to get better solution than what you are having right now. So the examples of this are integrated circuit designs. Now you see that there are many mobile phones are coming into the market. All of them use a lot of integrated circuits. Now these circuits involve not only thousands but millions of transistors and their connections. And you will see that almost say daily or say monthly newer models are coming out. So if you say that I want to design the integrated circuit in the best possible manner, maybe it will take a lot of time. By that time, other competitors will come out with better models and they will outdo you. So particle swarm optimization is to be used where you want very quick results. Need not be the absolutely best results, but better than what it is, and as quickly as possible, one has to use PSO, particle swarm optimization. Even though I said this, if you want to get best results, using particles form optimization, it is also possible at the hands of an adept user. Okay, so you need not think that it is a limitation, but in general, as I said, it is associated with a lot of speed. Similarly, particles form optimization is associated with a very quick results when you are dealing with a huge problem. Okay, so I hope now you know where to use it, right? So, as I said, concept of a particle. Let us say an automobile engine needs to be designed. We can consider it to be a particle. The particle will have lot many parameters. For example, even a bird has lot many parameters. It has wings, it has a beak, it has eyes, it has tail, it has legs, so many things. So, in case we consider automobile engineer to be a particle, engine to be a particle, it has type of fuel use, horsepower, revolutions per minute, so many, right? So, what is required is each particle can have various parameters. Now, I'll just discuss something which is slightly breaking from whatever I had discussed till now. So that's why I say seemingly unrepeated points, but I'll bring them together after some time. See, I would like to be in interactive mode now. Warren Buffett. How many of you know, or is there anybody who knows Warren Buffett? If somebody knows, please tell me, how do you know him? In what connection? I want answer. At least one of you should give me answer. Who is Warren Buffett?
So he is an investor, we can say, and he became very successful only by investing in stock markets, we can say.
Yes, very nice. So he is a legendary investor. Wherever he puts his money, that stock multiplies like anything. So he is a legendary figure in stock market, and there are many books, and he is very well known to people who invest in shares. Now I'll say that though Warren Buffett operates in USA, let us assume that Warren Buffett purchases some stock in India of Indian company. If you come to know that he is investing in some XYZ company, what will be your instant instant reaction? Would you inquire too much, or you would say, in case Warren Buffett has invested that money, let me also invest in that, because you believe in Warren Buffett, and Warren Buffett is known to be a good investor. So you are going to be sort of guided by his decision. Okay, I suppose you agree with me. Now, I'll now take another point. I'll join them after some time. But so remember Warren Buffett, and you feel like imitating him. Okay, he is a leader of investor, right? Okay. Now behavior of a novice carom player. Now you know, all of you must have played carom at one point or the other. Suppose you want to take a coin, you aim at it, and if you are a new person, quite likely you may miss the target, right? So, in particles form optimization, would like to imitate this behavior. Okay, how? I'll tell you after some time. So, now here again, I have talked about in my genetic algorithm. There is some of you may not know the film Sholay. There is one character played by Amitabh Bachchan, and whenever he will have dispute with his friend, he will say, "Let us use a coin and find out who will win." And it used to happen that Amitabh Bachchan was always winning. Reason is that his coin was same on both the sides. Okay, so it means that the randomness was not there, and so I had talked about this important to have good random number generator. So kindly note, in all the nature-based optimization, random number generator, if it is not good, then you are not likely to get good answers. So my caution to you is that whatever optimization technique which is based on nature, in case you want to use it, even before programming anything, first test the random number generator. It is a very, very important for the success of any nature-based algorithm. Okay. Now, I am again taking different point. As I said, I will connect them after some time. Concept of local based and concept of global based, right? Now, the concept of local based is something like this. You, let us say that you want to collect some flowers. You are in a garden, and at a distance you note a very nice flower. Of course, let us assume that you have the permission to pluck the flowers. It is not a good idea, but I am just taking hypothetical example. At some distance there is very, very nice flower, and just nearby you also there is quite good flower, may not be as nice as it. So probably there might be some obstruction for going to the best flower. You might feel that there may be some obstruction there. So there is a likelihood that you may pluck the nearby flower. So that is called local based, right? And but if you want the best flower, you will say, no, I'll go there. So both possibilities exist. So sometimes you will get attracted by, or you will take decision to sort of go in for the local base. Sometimes you will take the sort of decision, no, let me get the best. So there is a saying that, a bird in hand in better than maybe two in the bush. All of you know this. So this is the concept. So local based and global based will use it. Now, see what happens. As I said, now I'll bring the concept of carom player also, and the concept of global based and personal based, right? So now you know which is the global based, you know which is the personal based. You might get attracted towards personal base as well as towards global base, depends on the situation you are. So this decision can be randomized. Okay. Now you let us assume that you want to go to global base. For here it has been biased towards global based, so that's why you will see here. So you decide to go to this global based, right? But even though you decide to go to global base, because of some randomization, you will go nearby the global base. Okay. So this is decided by randomness of the procedure. Now let me kindly note what are points I had discussed with you. Let me go to the next. Now, one minute, just let me put up the phone. Just kindly hold. Just wait. Kindly excuse me for the distraction. As I said, this is from, I have given the source here. It's very readily available. So you can sort of refer to this. As I suppose you are able to see the source. Now this is from Eberhardt and She. This is a very, very important paper. Now this is sort of taken from their thing. Only the entire particle form optimization is swallowed in these 6 steps. Instead of reading, I'll just tell you orally. I'll describe it. So first of all, you create initial population randomly. Okay, I'll go on talking with you in an interactive manner. You have the idea how to create initial population. And usually it has been seen that the size of particle is usually 20. See, don't for simple problems. If the problem is complex, it can be 200, 2000, 20,000, 40,000, whatever it is. It depends on the problem at hand and the accuracy you would like to have. So in the beginning, you create some, let us say, I'll take the example of a 20, I'll restrict myself to 20 only. So let us assume that you are going to create these particles with their parameters in a random manner. Is this okay with you? At least somebody should respond to me so that I know I'm going at right speed. I'll repeat myself. In the beginning, you create particles with their parameters in a very random manner. Is it okay? Because these are very simple steps I would like to sort of introduce with you. Yes? Because I can read them, but reading has no meaning unless until I explain them. Kindly give me a very quick answer.
Yes, sir. Yeah, okay, sir.
Okay, fine. Then you find out the fitness of all those particles. I suppose this is also very simple. Then you know that out of all these particles, there is one particle who is the best. Okay, so declare him to be the best. So this best particle is something like your Warren Buffett of that population. Okay, and each particle will know its fitness, and individually it will say whatever is the, let us say for the first generation there is no history. So each particle will say that whatever is my fitness, that is my personal best. Okay. Now in this first population, you know who is Warren Buffett. Who is Warren? See, I suppose you understand the meaning of Warren Buffett. There is nothing like Warren Buffett of particles form optimization. I am using the sort of analogy to make it very clear what is happening. So I'll put it this way. In the particles, the swarm of the particles, there is one particle who is the best at that instant. So all other particles, what they will do, they will note that he is the best. So all of them might go toward the, will think of going toward the best. At the same time, when the particles are there, they will see that nearby position. See, there is one more concept, that is local best. I'll avoid it. So I'll just restrict myself to personal best and global best. Look, see, basically what happens, the flocks, the particle swarms are divided into some sub-swarms. So in that case, the local best comes into picture. I'll avoid that because that will complicate the issue. So I'm talking about the global best and personal best, right? Now, you create the next generation of particles by subjecting them to this rule. Okay, even though it is written in mathematical language, I'll explain it to you, okay, in very simple words. So each particle knows its position, so it adds to it the position which it knows where is the best of that generation. It tries to go there, but the distance is randomized. Okay, as I said, let us say that this wants to go to here, right? And the position, it also wants to go here. So this is indicated by C1 and C2 constants. Okay, I'll refer here. the decision to go, they want to go here and as well as go here, and this behavior is governed by this equation, C1 and C2. Now, please note, C1 and C2 are tunable in the sense at the hands of an experienced PSO user, he can tune them, C1, C2. But if you see the recommendation of Eberhardt, he says that in the beginning, you to be two without questioning. Okay, I would like to emphasize here, this equation looks very simple, but it has been arrived at conducting many trials using the mathematical knowledge and the behavior of a flock which the social scientist knows. Okay, so this looks absolutely simple, but they have gone through a lot of trials and errors. So basically what we should know that, let us don't question why C1 is equal to 2 and why C2 is also equal to 2. In the beginning, you take them to be 2 and 2, right? Then this is random number generator. Random number generator, as I said, has to be really random. Sometimes it will say, okay, you don't go toward the P base, personal base, but means the random number will be less, 0.1. And here in the sort of global base, the random number may be 0.9. So this position, new position will be biased toward the global base. But suppose the random number here is 0.9 and here is 0.1, the particle will go toward the personal base. Okay, so this cycle has to be repeated a number of times till you find that you are satisfied. See, please note, nobody can guarantee that you will get the best possible answer. So the user has to satisfy, yes. And I think here I'll say that, you know, I did talk to you, you want water, and every time you get water, first the glass is half full, then half up, half up, half. After some 5-6 steps, you will say, stop, let me drink the water, because you are thirsty. A person who wants to get some good design, he will stop at some stage, because, and the decision will be taken by the time available with him and the sort of answers which he is getting. So in short, this is the algorithm, very simple to implement. All what you require is random number generator. All what you require is, if there is a particle, is the swarm of particle who is the best there, and the idea that if somebody, one particle which is the personal base for it right now, if the personal base from the previous generation was base, then he will say his personal base will be modified to the previous base position. Okay. Similarly, global base is, if there is, suppose, say, you know, in generation 5, there was some particle was best till that time, and the next generation, the best particle is not as good as the previous generation, then the best, global best will be modified to take the value of the previous generation. So just remember, the global best is always best till now. Personal best is the best for the particular particle till now. Okay, so I would like to get some response from you. I would say that the behavior of a particle is governed by this equation, and these two are random number generators, random numbers. C1 and C2 are also tunable at the hands of a programmer, but in the beginning you keep them 2 and 2. Now don't ask question, because this has been arrived at after a lot of experimentation. So you also take it to be 2 and 2, and after some time, when you get confidence, you modify them. Then here is a local base, and this is the global base. Okay, so you, in short, I had to tell you that the particle will will try to go toward the global base with some randomness, and also will try to go toward the um, local base or personal base with some randomness, and the final decision will be addition of these two, vector addition of these two. I'll just explain that. See, this is the global base, this is the personal base. So the particle would like to go towards this with some randomness, and will go toward this with some randomness. Now, in this picture, you will say that it has been biased toward the global base. But suppose if it had been biased toward the personal base, you would have seen the arrow like this. Okay. So here comes the, what I said, carom player. He is trying to go here, let us say, but he will miss the target and go here. Now, what is the purpose of this randomness? Randomness purpose is that even though this is known to be a global base, but quite likely nearby the global base, there may be better candidate. If you are in a Himalayan region, and if you are climbing the hill, and you have achieved some very good height, you should not think that you have achieved the target. Quite possible that if you move further, there will be another height which will be better than previous one. So therefore, this is at the heart of success of the particles form optimization, that you go on exploring newer areas near the supposed to be global base, and also go on exploring nearby areas. Quite possible there just nearby there may be global base for the next iteration. So I would like to stop here in the sense I would like to get your response, because I'm just talking. I would like to know whether you are getting the hang of it. At least one of you should respond. Yeah. Should I repeat? I'll repeat. At any, see, there are two positions. One is personal based and another is global based. So now I am assuming that you have crossed the zero population first to. So right now I assume that this is the nth population. Now the decision of each particle will be governed by the equation which I have mentioned here, and the parameters will be the particle would like to go toward the global base with some randomness, and also try to go toward the personal base with some randomness, and the final decision will be vector addition of these two. There it will be new position for the next generation. That will happen for each and every particle. Is this clear? If it is not clear, I would like to try to make it clear. I want your response.
Hello, sir. Hello.
Okay, no?
Sir, so how we are deciding the global based or personal based, like for using fitness function?
Yes. Yeah, because finally we are going to see, how do you say that, he is a topper? Suppose, in a university, somebody receives gold medal. You are not going to see how many marks he got in subject 1, subject 2, subject 3. You will say, what is your overall sort of total? Based on that, you will award him sort of that gold medal. Similarly, you are right. When we say that this one particle is good or not that good or the best, is wholly decided by the fitness function. And as I said, the idea of fitness can be a dynamic. I think I have already elaborated on this. So this fitness has to be awarded by you. So when you are reaching the final stage, you might revise the criterion of fitness. For example, in Olympics, the final is fought neck to neck with maybe 0.01 second. But in the even before reaching Olympics, people sort of do their running races in their local places. So there, the criterion will not be that harsh. Okay, did I answer your question?
Yes, sir. Yeah, got it. Thank you.
Okay, so so can I assume that the philosophy, I am talking the philosophy. If you want equation, these equations are here, and I have already given you source, and I have already explained you what these two equations mean, correct? And I have also told you don't question the C1 and C2. Take them as they are recommended, because that is the wisdom they sort of acquired after lot many trials. After getting your own wisdom, you may tune them. And I would say one more thing. These two equations are the very basic equations of particles form optimization. Many things have been introduced into them afterwards. So in fact, you'll see that the literature is quite sort of, there are so many parameters have been introduced into these two equations. But for a beginner, one must start from here, gain experience, and then go on introducing some new parameters. There is no limit to it. Okay. So I will assume that now you know what exactly is happening in particles form optimization. Now let me, these are what I had already talked about all these points. See, initialize population in hyperspace. Now this is a mathematical language. Evaluate fitness of individual particles. Modify velocities based on previous based and global or neighborhood based. See, neighborhood based comes when you have a very big swarm, and you have that big swarm has small, a number of smaller swarms. In that case, the neighborhood comes. Okay, so I don't want you to get confused right now. So don't, as you become expert in the particle form optimization, you will also get introduced to this neighborhood afterwards. But right now you ignore it. Terminate on some condition, go to step 2. This is as simple as 2. And this slide is from Eberhard, the creator of this algorithm. I'll just tell you one thing. Within no time, this paper, the paper is only a 3 or 4 pages. Kindly note. It's very easy to understand, and within no time it got 50,000 citations, which is exceptional. Okay. Now let me just show you. These dots are particles, and they try to go toward what is supposed to be best. Now just see here, they are all randomly positioned here. Now you see, after some generation, they come here. Okay. So kindly ask me any questions. See, I'm not able to hear you. If somebody is able to hear you, somebody can repeat it. Kindly excuse me, I am not able to hear you.
I think the voice is very low. If you can type, it would be nice. If you cannot speak louder, you can type. Maybe it's not.
Good morning, sir.
Okay, very soon.
Good morning, sir.
Yeah, I am able to hear you. Good morning. Good morning.
Sir, this is Shobana from Pratyusha Engineering College. Where and all we can, where and all we will get correct output. That means where and all we can use PSO technique, sir.
See, I have said this a number of times. Nobody can guarantee you that you will get best results, but there is a good chance that you will get as best as possible. For example, when you go to a shop and try to buy some item, that item has not been, is not known to you. But if the shopkeeper there, who is known to you, tells you, hello, sir or madam, buy this, I am giving my word to you. Similarly,
Yes.
all these optimization techniques, they tell you please use us or these techniques. We try to give you as best as possible, though we don't guarantee that you will get the best. And for that matter, no nature-based algorithm. Please note the words nature-based. I'm not talking about the mathematical calculus-based algorithms. If you are going to use nature-based algorithm, mark the word again, nature-based, you are not likely to get the best, but near the best. Did I answer your question?
Yes, sir. Yes, sir.
Yeah. You will get better than what you have. And depending on the time you at your disposal, you can decide when to stop. Yeah.
Okay.
Any other question? Okay. So, just tell me. So, can I move now?
What reference book would you prefer for us to read regarding the PSO?
Somebody is talking, but I'm not able to hear.
The voice is too low.
Yeah. No. Still, the question is not audible to me.
I think it's Amol Dalabi. Amol, are you trying to speak?
Okay. So I think since the question is not audible, maybe that person can
Type.
email me. Yeah.
Type it in the chat window. Yeah.
Yeah. So should I move to the next topic?
Sure. Sure.
Okay. So let me 1 minute. Just let me share the window. Okay. The new window is visible now.
Yes.
The title is "And Colony Optimization." Is it visible to everybody?
Yes, sir. Yes, sir.
Yeah. 1 minute. Let me advance it. The title of this topic, which is again part of the swarm optimizations and colony optimization. Now, and colony optimization is sort of AS is the acronym. It was proposed in 1996. Okay, 1 year later than the particle form optimization. Now, the person who is associated, he is the main person, Dorigo. He is from Belgium, but right now he is in MIT. So he studied ants and proposed ant system optimization and colony. It is known as ant colony optimization afterwards. Ant colony optimization, it is popularly known as ACO. Now, what is this? It tries to imitate behavior of ants. Just for your information, nature-based algorithms are based on some natural observations. It can be with respect to ants, it can be with respect to fish, it can be with respect to birds, it can be with respect to honeybee. There is another very popular algorithm which is nature-based, is honeybee. Now, you must have seen that cuckoo has some very peculiar behavior. It never lays its egg in her nest. That cuckoo puts the eggs in others' nest. Okay, so this has been used to get the sort of algorithm. There is bat algorithm, firefly algorithm. Okay, so ant colony optimization is quite well known. So let me talk about it, which is a part of swarm optimization. Now, see, you find some very interesting behavior of ants. See, they are making living bridge. So from this position to these positions, there is nothing except ants together. So this is something very sort of not very usual behavior. So you will definitely note it. Now, if you see that this is a big leaf and ants are able to take it together Now, please note, each ant is exercising force in such a manner that the resultant is able to move this leaf, which is sort of weight is much more than individual ant. So if they don't exert force in a particular direction, they will not be able to succeed. But they are in a position that in a group, they are able to move this leaf. So this is cooperative carrying. Now, as I said, this is very important reference. You can look at it, okay, for many details. Now, what exactly, as I said, now I'll slightly sort of divert about Ramayana incident. Almost all of you or many of you may be knowing Ramayana, and there is abduction of Sita by Ravan. Then when he sort of abducts her, she goes on throwing from the supposed to be a plane at that time, her ornaments on the ground. Periodically, she throws her ornaments on the ground. The idea was her ornaments will be located by Rama, and he will know by which route he has gone. Okay. Now, this is just to sort of make you the understanding interesting. Now, I'll just see, kindly note, I'll be talking slightly in a disjointed manner, not in a very continuous manner, but I'll combine them together after some time. Now, this is the concept of stigmergy. This you will find this word used in optimizations as swarm optimization. Stigmergy is a mechanism of indirect coordination through the environment between agents or actions.
देखते हैं sir.
Yeah. So stigmergy is a form of self-organization which produces complex, seemingly intelligent solutions without need for any planning, control, or even direct communication between the agents. For example, see, there may not be direct communication between this ant and the another ant, but by cooperation, they are able to achieve this feat, right? Similarly, there is ant here, or there are some ants there also. They may not have communication, but together in a group, they are able to cooperative manner achieve the target, which is otherwise difficult. Okay, so stigmergy is a form of self-organization. For example, you saw that bridge. They organize themselves in a nice manner. It produces complex, seemingly intelligent solutions without need for any planning, control, or even direct communication between the agents. This is known as stigmergy. As such, it supports efficient collaboration between extremely simple agents who may lack memory or individual awareness of each other. Okay, so this is the concept of stigmergy, and it is noted in case of ants. Now, let us talk about the pheromones. Now, I did mention to you the Sita in Ramayana. Sita was throwing her ornaments on the ground. Now, very similar thing happens when ant moves on ground or on any surface. The ants deposit so-called pheromones. Okay, it is a known fact. The ants, when they sort of travel some path, they go on depositing pheromones. Then these pheromones are useful for other ants to get some idea, and these pheromones, they get evaporated after some time. So kindly note, ants, when they travel their particular parts, they deposit some chemical things on the path, and that chemical deposition, after some time, it doesn't evaporate instantly. After some time, it evaporates. Okay, this kindly note this. Now, if there is a choice between alternative path, an ant would have the tendency to choose a path having higher deposition of pheromones. I'll now explain this behavior of an ant with these two things. Behavior of a small baby. Okay. Now please note what I'm doing now. I'm trying to explain the behavior of ant with whatever we know in our sort of day-to-day observation. Almost all of you must have seen a very small baby, maybe 10 days old baby. If somebody calls that baby, do you think that the baby will look at him or her? Unlikely. That baby may just look here, there, but will definitely not look towards the person who is calling that baby. So a small baby just does not get attracted towards or does not try to focus the attention toward the person who is calling her, right? So this is behavior of a small baby. Now, so there is now, let me talk about the behavior of an intelligent adult. Imagine that you are in a small boat, alone, very small boat, and because of the sort of currents, you land yourself in an unmanned island. Okay, so this is a hypothetical situation, but you imagine yourself, you are alone in a boat, you have landed on an island which is having a lot of jungle, and you sort of try to find out whether there is any shelter or not. You slightly go inside, you are surrounded by jungle, and you are afraid. You climb up on a tree, and you are able to see the possibility of a human being because you note some path and you note some footprints of a human being. Now, what will come to your mind? Your first thinking will be that yes, there is some human being here. Let me go and approach that human being. Okay, this would be one thought process. Another thought process will be, oh my God, he may think that I have come to attack him. So he may be hostile to me. So what decision you take will depend on your thought process, which may be sort of decided on the spur of the moment or randomness of your thought process. So basically what I would like to say that a small baby would not like to look at the source of noise, right? It will ignore that source of noise. Similarly, intelligent adult may not choose what may be a good option. He may even reject it. Did I make my points clear? Because this is at the heart of the behavior of ant. I want your response. I'll repeat myself. A small baby may not look towards the source of sound. I'm talking about a very small baby. I'm not talking about 1-year-old baby, right? So then behavior of an intelligent adult, he may get into dilemma whether he should go in one direction or he should avoid it. Now, is this clear?
Yes, sir.
Okay, nice. I am very happy. So behavior of ant is governed by these two elements also. Now this picture is before you. Please note an experiment was carried out by Dorigo on ants, which are known as Belgian ants. Okay, there is that particular species is known as Belgian ants. So ant is an ant, but this experiment was carried out on Belgian ant, and all of us assume that the behavior of Belgian ants will not be different than that of Indian ants or American ants. Okay, but the source is experiment carried out on Belgian ants. So this is an ant. Then these are the direction in which that ant will go. Now, there is a deposition of pheromones on this, because previously some ants have gone by this way. There are many ants which might have gone here. Few ants might have gone here, and maybe 1 or 2 ants might have gone this way. So you will say that the deposition here may be highest, lower here, and very small here. So the ant is here, and it has the 3 options. Quite likely, it would go toward this, where the pheromones are, deposition is more. But now imagine that ant will have sometimes the behavior of a very small child or intelligent animal. It may say, it may randomly say that no, I'll go here. Or sometimes it will say no, if there is one more path possible, then say no, I'll go by this way. Okay. So the behavior of an ant is captured by mathematical formula. It is given here in this paper. Okay. So basically what it means that you have different options at particular instant for a particular ant, right? So you should imagine that there is a colony of ants here, there is another ant 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 here. Let us assume that there are 100 ants in their sort of home. Okay, now they come here, and previously ants have gone by these 3 routes. Let us assume. Then when an ant comes here, it may follow the route which is having lot of pheromones. It may go here. Another ant will come. It may randomly say, hello, let me go this way. But the possibility of going this way will be less. Okay. So similarly, this is a sort of having sort of not the best, but in between. The possibility of the ant choosing this path will also be proportionately less. But again, please note, it will be randomly decided, right? And the decision here will not be exactly proportional to the pheromones, but it will be randomly proportional to that. Okay, so quite often it will go here, sort of next to, after this, the another ant comes, may choose here, but once in a while, and only 1 or 2 ants will go by this way. Okay, now this equation is given here, that and that equation has the base of experiment carried out by Dorigo on Belgian ants. Okay, but as far as I am concerned, I would like to tell you that the behavior of ants is given by is described by one formula given in this paper, which takes into account the pheromones deposited and what any ant will come and go by this way. Now another ant comes. Since now this decision is randomized, the next ant will not go exactly by this route, but it may choose another route. Okay. I would like to wait here. How an ant will choose the path? Is it clear?
So hello.
Hello. Yeah. Is it clear?
So how can we can make like it analogous to what, like the small baby or the adult man?
Both. See, small baby does not look at the source of noise, sound. It ignores the source of sound. But sort of baby which is 2 years old will definitely look toward the person who is calling her, right? So, and also similarly, the intelligent person will also not get attracted to, as I said, that if you are in a sort of a land, sort of island, where you see possibility of a human being there, your instinct will be to go toward that human being, but you will also be afraid, right, to approach that human being because he may be hostile to you. So the decision is not necessarily governed by the, if somebody's human being is staying there, you feel like going, but you may not go. So it's a decision not governed by the sort of what would be the best solution for you, but will be, you may reject that. So
That's
for example,
that's why.
I'll just tell you.
Yeah, sorry.
I'll just tell you, this is the best road. The ant will have tendency to go here, but it will reject it and go toward this. Is it clear now?
Yes, sir. So, like we can say, sir, ki, so that's why we are saying ki the whatever the path they will follow, that is random. That will be randomized.
Yes, yes. But random, but again based on certain natural phenomenon of ants. Okay. So
Yeah. Yes,
ants
sir.
have the, for example, I'll tell you one thing, one very sort of a personal experience. A friend of mine went to Andaman. Okay. And he is a nature lover. So he sent me some photos of some nature also, and also of the floor of his room. Why did he send it? Because some food particle was left by mistake on the floor. When they came back to their hotel room, they saw a line of ants. So when that food particle was left on the floor, they did not announce to the ants, hello, ants, here is a food particle, you come and pick it up and make a beeline line. So it means that the ants were moving there randomly. One ant noticed that, it came back and it told other ant, hello, I have come back with a food particle. You follow my path, you will get another food there. So after some time, there will be line of ants. See, the line of ants finally was there because of the deposition of pheromones. And in the beginning, there was no pheromone. So the ants, of course, the ants were there in the rooms, but they were wandering randomly. Okay. Did I make it clear?
Yes, sir. Yeah. Fine.
Yeah.
Thank you.
So in short, one sentence I will tell you, the ants have the ability to wander here and there. That is basic, and they don't abandon it at any point of time, right? So, but they have also the tendency to go toward the pheromones. Now, these are conflicting things. Sometimes they may say, look, I'll go to the pheromone. Sometimes say, hello, why should I go to the pheromone? There may be another good source. Let me go in this direction and get that food, which may be better. Okay. So I'll now just shift my screen and try to show you YouTube video. I suppose I am successful in sort of connecting it to that YouTube video. Is this visible to you? 1 minute. I don't know how to. Just hold on. Huh? Kindly wait. Let me share.
You want to make it full screen?
Are you able to see YouTube thing?
Cannot.
Control plus L, sir. Adobe Acrobat, Control plus L. Control key plus L.
Control plus L.
Yes, sir.
Is it visible?
No. So what you need to do is you need to share another window. So on the bottom, you have that share button, right?
Okay, yeah.
So you click
1
that
minute.
share.
Yeah.
And on the
1
right
minute.
side, you will see your YouTube pop up. You click on that.
Just hold on. Kindly excuse me for this. Let me go back to.
So you click on that share, it will open up a new window. And on the right side on that window, on the left side is your desktop. So you can share your desktop, or on the right side, you will find your YouTube window, the appropriate YouTube window. So either you can share your whole desktop or you can share the YouTube window.
Yeah, 1 minute. So I'll just minimize this. Okay, now Kindly excuse me because this is something I did not expect actually.
So you can paste the link here and I'll open the link and share.
Okay. And again, pasting is difficult for me.
So you right
Okay,
click,
I'll just,
you right click on
Yeah.
that link.
uh,
On that PDF, you right click on that link, copy link.
yeah,
Can you
1
see
minute.
copy link?
1 minute, just hold on.
Can you just put up your slide, your PDF, and I'll start the.
Okay, yeah, 1 minute. I'm not able to get to the,
PDF?
yeah, no, should I join meeting again?
No, you don't need to join. You just go to the bottom of your screen on the taskbar and click on that PDF. It will open up again.
Okay, 1 minute.
On the bottom of your screen, there is a taskbar.
Right.
You click on the
Yeah.
PDF.
Correct.
You go to that page where the link was there.
Yeah, 1 minute. Now I know. Now this is the link.
Yeah, okay. So let me just type it, https YouTube
Dot.
/simu6 m7ftxe.
E small. XE.
Yeah, so now I'll share this window, right?
Okay. Yeah.
Okay, so you will be disconnected for a while.
Okay. Yeah. No problem.
Okay. So can people see this window?
Yes. You can start.
Okay, so I'll start playing, right?
Yeah. Right. I think you can go back. Yeah. Start. Right.
So let me
See
comment
two
pause.
hands. Yeah.
Maximize. Can you like zoom in?
Okay.
YouTube, yeah.
It doesn't matter actually. Hands need not be
Is it
maximized.
better?
Yeah.
Yeah, yes, sir. Yeah.
Okay. So Professor Shimpi, do you want me to stop here or do you
Yeah.
want? Okay.
No, yeah, it's okay. I can also talk. The two ants are coming from this, and there is a food somewhere. And for reaching the food, there are two paths. Am I audible
Yes.
now? Yeah. So yeah, you can continue. Continue the video. See, the one ant has already gone to the food source. Second is moving slowly. Not speed is same, but the distance is more. Now these dots are pheromones. The ant has got the food, it is coming back. The second ant has yet to reach the food. Whereas now the pheromone deposition on the ant number 1, that B1, is sort of more. Now, yeah, you can move. Yeah. So it will follow this. Now, since the pheromone was more there, even the second ant is now following that path. So you can see that on the top root, there is more pheromone deposition, right? So I think you can end the things. Now you can disconnect and connect me.
Okay. So you will need to connect yourself.
I see. So should I say share?
Yeah.
Then window, then yeah, we were here. So this double bridge demo you saw, am I audible?
Yes. But we cannot see anything. It's a gray screen. So you need to re-maximize your PDF, I think. If you click on your PDF.
Yeah, right. 1 minute. Is it now?
No.
Quickly there?
No. So stop sharing and share. It is visible. Okay.
Visible. Okay, fine. So this is you saw that. See, any questions on the demo? See, the path traveled was the sort of having deposition of more pheromones, right? but still the longer path still has some pheromone. So but the tendency of new ant will be less. But suppose that there is some obstruction in the shortest route, then the ant will not be able to deposit the pheromone there, okay? And the pheromone which was already deposited there will vaporize after some time, okay? So if there is any obstruction on the base path, now since the deposited pheromones will get evaporated, the new ants are not likely to follow the previous short path, right? So they will follow a longer path, but which is the only path possible. See, is there any question on that? I would like to get the feedback or questions. Am I audible?
Yes, you are.
Okay.
Yes, sir.
So, any questions? Okay. So, I'll just repeat. The purpose of pheromones is to bias ant towards a path which is having more pheromones, right? And the purpose of evaporation of pheromone is that if suppose that path by some chance happens to get obstruction and that path is no longer a viable path, in that case, even though the deposition of pheromones is higher in the beginning, after some time the deposition will get evaporated and a new ant will not get biased toward that path. So it will become abundant path. Now, what should be the rate of evaporation is to be used by the user. Again, the sort of guidelines are given in the paper I have given. But after using the path, after using the algorithm, one gets sort of some insight into it, and then he can tune it. See, please note all these algorithms, whether genetic algorithms, simulated annealing, particle swarm optimization, and colony optimization, they require some training. As far as the user is concerned, he has to solve some demo problems, get experience, and then we can adapt in using it the way he would like to use it, right? Now, let me, is there any question till now? Because I have yet to cover some points about ant colony optimization. Is it okay? Has been understood or roughly understood?
Yes, sir. Yeah, understood.
Okay. Now let me come to the sort of pros and cons of SEO. The ant colony optimization is very successful when you have got clear-cut choices. For example, if you are at the junction where say 4 or 5 roads meet, you have clearly 4 or 5 choices. But if you are in a field, how many chances you have got? Infinite, because there is no road. So ant colony optimization implementation is easier when there are number of clear-cut choices. Kindly mark my words, clear-cut choices. Now, just to give demonstration, analogy, if you are standing at the junction of a road where 4, 5, 6 roads are meeting, you have clear-cut 4, 5, or 6 choices. Okay, but if you are in a field, open field, let us say football field, if you are standing in between the field, you have got many choices. The choices are infinite. So ant colony optimization is very difficult to apply when you have got infinite sort of alternatives or very large alternatives. But in case you have got limited alternatives which can be counted 5, 10, 15 like that, then ant colony optimization is very successful. For example, if you are at a fire station and there is some fire at some place and you are the chief firefighting officer. At your command, there are some 2-3 fire stations. If you carry out ant colony optimization, you will be able to immediately sort of course, I am talking a hypothetical thing, right? Sometimes the decision have to be taken by the human being involved instantly without running any algorithm. But I am just sort of to give the suppose there is enough time for you to run some algorithm. Then, if you run ant colony optimization, it will tell you, okay, this route is blocked. You go by that route. So it is possible when you have got sort of clear-cut number of alternatives, you can come to decisions quite quickly using ant colony optimization. It is not a choice where you have got infinite choice, then ACO is not a really good candidate. So this is the limitation of ant colony optimization. Yes. Now you can ask me. You can ask the questions. 1 minute before I finish my thing. See, here you saw that optimization demo. Here is another. Visually, you can see that these are the two paths. One ant is going here. You will see that ants are going here, and you note that one ant is here also. Is it visible? My pointer.
Yes, sir.
Yeah, there is one ant here. Now this ant, when it started from here, it had the choice to follow this path, right? But it said, no, let me go here. So this is the behavior of a very small baby, of a very intelligent adult who might feel that, the best solution may be having some danger, right? So this ant is responsible for depositing some pheromones on this route. In case there is obstruction here, right, this deposition will help in finding this route. Is it clear now?
Yes, sir.
Okay, nice. So I'll also, now this is a two-dimensional thing. Now this is a sort of well-known problem, what is called traveling salesman problem, right? So there are a number of cities. You would like to visit all the cities in a very shortest possible time. So these are possibilities. These are possibilities, correct? This is the solution actually, right? So this is the three-dimensional picture of how the ants can move in the 3 dimensions. In case you are designing having 10 parameters with, of course, distinct alternatives, then it will be problem in n dimensions. Okay. So I have come to the end of my presentations. If there are any questions, I would like to take them. Kindly ask, or if it is clear, tell me so. Please don't shy.
Yes, sir. Clear, sir. Today.
Okay, nice. So I will tell you one thing. I have come to the end of my presentations. So the goal which I set for myself is this, that I should introduce the algorithms in sort of in a very friendly manner, wherein you know the algorithm and you have the confidence, yes, you can deal with them. Okay. And after using them, you will become expert in that, and you will also be able to modify them. For example, particle swarm optimization, if you see the literature, it is replete with small, different modifications. But see, then in case you have got a full course on, let us say, particle swarm optimization, it is worth talking all about them. But in case one wants to know, there is no other way but to follow Eberhardt's paper. Actually, there are three papers I have sort of given there. Eberhard Kennedy, 2 papers, Eberhard She, 1 paper, which is I use that explanation I use from Eberhard She. These are very basic papers and very simple papers. The papers are of the very first paper is of only 2 or 3 pages, right? But they have become landmark papers. Like E is equal to MC square. How many pages it occupies? Not even 1 page, not even 1 line, but E is equal to MC square is unmatched in its importance, right? Similarly, sort of very short papers by Eberhard Kennedy and Eberhard She are unmatched in their importance, even though they are not lengthy and even though they are not mathematical in nature, though the formula which they gave, they really slogged before putting those formulas. So I wish you good luck in your endeavors to optimize the problems, and you acquire different algorithms. For example, if you are Army General, you would like to use your artillery at some time. You would like to use aerial bombing at some time. You would like to use your soldiers to use rifles at some time. You would like to use them machine guns at some time, sometimes heavy machine guns, sometimes light machine guns, right? Depending on the situations. So similarly, I expect you to sort of deploy appropriate algorithm for the problem at hand. I wish you good luck. So, Professor Akshay, I have come to my end of my presentation.
Yeah, thank you, Professor
As-
Shakti, for this wonderful
as-
talk. You have
as
just
concluded,
finished in the right time.
Yeah.
Just right. So it seems all the doubts have been cleared. Okay, then I hope you will be with us for future workshops and share your knowledge with us.
Pleasure.
Okay, then. So I'll close this session. We will again meet at 5 p.m. in the evening. Thank you.
Okay, sir. Thank you.
you,
Thank
sir.
you very much.